guys, in this video tutorial I would like to explain that how we can find the lower bound of the variance of an estimator. Normally we were talking about the estimator, that the estimator is better which has less variance, but we don't know how much that variance is less. What is the lower bound of the variance? So in this video I would like to explain, I would like to find to derive the formula that how and what is the lower bound of the variance of an estimator, and then we will have an example maybe in the next lecture, because this will be lengthy, that how we can determine that estimator for which the variance is for which there is lower bound of the variance. So we will compare the variance and the lower bound in that lecture, that if for some estimator the lower bound is also equal to the variance. So let's start. This is sometimes difficult to find the lower bound normally, but under some condition it can be possible to find the lower bound of the variance of an estimator. These conditions are called regularity conditions. Regularity conditions. This means that the distribution which satisfy these conditions, these regularity conditions, I would like to write these regularity conditions. Number one, the range of the distribution this means the probability distribution, of course, nowhere depend on the parameter. Number two, all relevant derivatives of the likelihood or log likelihood exist. Third, all relevant integrals of the likelihood or log likelihood exist, and the order of the derivatives and integration can be interchanged. Integrations can be interchanged. So this means that the distribution, the probability distribution which satisfies these three conditions, they are called regular distribution, and the distribution which don't satisfy these conditions, they are called non-regular distributions. So you can see, you can check. The most important one is the first one, and you can see that the distribution which involves the range, then the distribution which has a range that depend on the parameter, this means that that is non-regular distribution. And this is for non-regular distribution there is a different way to find the MLE. I will do that sometime later, but now we are moving toward to find the lower bound of the variance. So before, these are some conditions. This lower bound you can find for regular distribution, and now I need to prove some lemmas before going to the proper proof to find the lower bound. So now I need to prove lemma, that is we call lemma 1, because the result of these lemmas will be used in that proof. So I need to do that. Lemma 1 says that expected value of the first derivative of the log likelihood with respect to parameter theta is equal to 0 for all theta belong to the parametric space. For all this belong to the parametric space. Okay, so now let's prove this lemma. We prove this lemma. This lemma for continuous case and we can say that this means that x is the variable is continuous, so you can start like this: x1 integration with respect to x2 and integration with respect to xn, f of x1 x2 f of xn dx1 dx2 dxn. In short, we can write this like x, this represent all those x, this x, and dx. This means these represent all x. Since f of x is the joint distribution of x, this is of course the joint distribution, since this f of x is the joint distribution of x, therefore we can say that we can write that the integral in this dx is equal to 1, as we know this from the probability theory. Or you can say that x, and this is, you can say, the likelihood function as well. So this is equal to dx equal to 1. You can write like this as well. Now differentiating with respect to theta, we get differentiating with respect to theta, we get differentiating this with respect to theta, we get. So this means that just apply partial derivative for this on both sides, dx is equal to partial derivative of theta of 1. This means that you can see, you can write like this: partial derivative with respect to theta, x theta dx, that is equal to 0 because this is constant. So you can see that now you can do this like divide and multiply this by L. 1 divided by L, you can say Lx theta, or you can say L, so does not make difference. You can write this like, okay, let's write in the full form. So this theta n2 by the same thing you can write here, x theta. So this is one thing. I just divide this and multiply this with this one, and now multiply, this is divide, so multiply, so that this has no impact. Dx is equal to 0. Now you can see that this thing is equal to, you can see that this thing you can combine by this bracket. So you can see that this you can express now x, and this is partial derivative of the log likelihood now. Log likelihood now. So this thing you can now express like this. I will explain this. Now you can see like this, and this is theta dx equal to 0. I will write on the side this to explain how. You can say log L theta. So the derivative of this is del by del theta is equal to, this is equal to 1 divided by L. You can say, I don't want to write this in full, so just L, and now by del the partial derivative with respect to L theta. That is why I just back this step. This is forward, I am doing this, and this was I was given this. This is like this part, and then I went one step back, so I mentioned like this. So now you can see that look at this. This is the expected value of this one, simply expected value of this thing with the partial derivative, of course. So this means that this is, you can say that this is the quantity and this is the distribution. So this you can say x, and this is the distribution. I will write this. So this means that this is the expected value of partial derivative with respect to theta. This is of course natural log. So you can write, I will just want to explain this. This you can say okay, I can choose from here. So this is x theta, and that is equal to 0. You can say this, you can write like this. This is just like, if suppose you write x f of x dx, that is equal to e of x. So you can say this is the x quantity and this is the distribution f of x, and then so this is lemma is proved now. This was, we want that, so this is proved. Now lemma 2. Now we need to prove lemma 2 before going to find the lower bound of the variance of an estimator. Lemma 2. Lemma 2. What this lemma says? This lemma says that we need to prove that expected value of partial derivative with respect to theta of the log. I will not write Lx into theta, I will just say L, just mention in this like in this lemma, because this will take time, so I can just write L. So this is natural log of the L. This is equal to minus expected value of second partial derivative with respect to theta square log is equal to variance of del by partial derivative with respect to theta natural log of L. So I need to prove now this. Okay, prove. Now we can start from lemma 1. We have a result. From lemma 1, we have our results. A result, that is expected value of this, I will say log only L instead of log Lx theta, that is equal to 0. Now you know that variance of partial derivative with respect to theta of this is equal to expected value of partial derivative with respect to theta log L square minus expected value of log partial derivative with respect to theta log and whole square. This is just like the variance of x is equal to e of x square minus e of x whole square, just like that. So remember this formula, basic formula, so you can know. And you know that this thing is 0, so square of 0 is 0. This means that variance of partial derivative with respect to theta, so log is equal to expected value of the partial derivative with respect to theta natural log whole square. So this is equation 1. Now again from lemma 1, yeah, lemma 1 is very helpful in this case. From lemma 1, we know that expected value of partial derivative of natural log L is equal to 0. This means that this is equal to, you can write this like, again we need to go back, that is L n to L dx is equal to 0. Remember, I'm just going one step back. This is equal to this quantity into the distribution, that is mean like the joint distribution or the likelihood. Differentiating with respect to theta, we get differentiating we can differentiate this, that is partial derivative with respect to theta, and now we can do this by partial derivative with respect to theta natural log this thing and then L. So this is thing we need to differentiate with respect to theta partial, that is equal to 0. So now we need to use some product rule of the differentiation, that is f dot g. There are two functions f and g, and we need to differentiate this. This means that differentiate this remaining g plus f as it is and g differentiate g. So this is some rule from calculus. Now using this rules you can do that. Partial derivative with respect to theta of this, and L will remain there as it is, plus now you need this will remain as it is, and you need to take the derivative of this L, so this L become like this, and this is equal to 0. Now you can see that you can write this like partial derivative square with respect to theta square, natural log of L n to L plus, you can write this, just write this as it is, like this, and multiply and divide this with the L. So this means 1 divided by L, partial derivative with respect to theta, and multiply by L. And remember that you need to write dx with both dx equal to 0. Now you can write this just want to check one thing. One thing you remember, that this was not log L. Remember this is important, you need to remember. This second term is not with log L. So this is mistakenly I mentioned this. I need to remove this as well. This is some correction, you need to do that. So this is L because we are taking the derivative of this, and this is L. So you can see that now you can write this. This is okay, this is as it is, x n to L dx plus, now you can write this as, and you can write this now, this quantity now, like this. Now you can write this with natural log L dx equal to 0. So now there is some pattern, you can see that this is now equal to log L dx plus, now you can multiply, these two are the same things, so this will become now square L equal to 0. So now there is some, you can find some relationship, I mean some pattern in this now. Now you can do this. You can see that this quantity, the first quantity is the expected value of this, and the second quantity is the expected value of this. I explained this earlier, so you can write this as the expected value of and this is equal to the expected value of this. This means that this is, you can say, you can write this on that side, so it does not make difference, or you can write the plus. You can directly write on the other side, does not make any difference. Expected value of square, but this should one of them should be negative. So if you write this on the other side, this should be negative. If you write this on the other side, that should be negative. It does not make difference, so this should be negative because you are shifting this on the other side, so that is negative. Now this is equation 2. Now from equation 1, you can see from equation 1 and equation 2, you can write what was equation 1. You can just maybe go back and you can see what was equation 1. Equation 1 is this one. This is equal to variance of this. So this thing is also there. This thing is there, that is equal to minus E of something. So this thing was equal to sum of the variance. So now you can see that from equation 1 and equation 2 we can write variance of this quantity is equal to expected value of, with respect to this, square is equal to minus expected value of with this quantity, and this is the proof. So this was required. So this is lemma 2, and we will use the results to find the lower bound of the variance. Now for the lower bound we need to use Kramer-Rao inequality, that is also called lower bound. I will write the statement first and then Kramer-Rao inequality. Kramer-Rao inequality, or say lower bound. Remember, lower bound is for variance. Remember, lower bound of the variance. I will just write the statement first. I will write this likelihood function. This is the likelihood, denote the likelihood function. L denote the or you can say L theta, denote the likelihood function. The likelihood function corresponding to sample x from of x theta from some distribution where theta belong to the parametric space, and assume that f of x theta satisfy the regularity condition. The regularity conditions. Suppose Tx, that is denoted, we can do like this, Tx is an unbiased estimator of some function of the parameter. We denote that by this, which is a function of theta, yes, which as a function of theta. Then the variance of Tx, this estimator, remember, unbiased estimator, is at least phi, that's mean you can say this quantity divided theta, this is squared divided by variance of this quantity. So the variance of this estimator Tx is at least this one. At least mean this is the lower bound. So we need to prove this, and then in the next lecture we will try to find to solve some example where there is some explanation now where variance of this quantity is also equal to expected value of square. This is also equal to minus expected value of, this is from lemma 2. In other words, briefly we can say variance of Tx as at least mean greater than or equal to square divided by like this. So we need to prove this. Let's start the proof. I hope you understand the statement. Just let's see once again what the statement says. Same statement, I think. Okay, whenever I have inequality or lower bound, we can select L theta denote the likelihood function corresponding to sample x from some distribution f of x theta. Theta belongs to some parametric space, and assume that f of x satisfies the regularity condition. Suppose Tx is an estimator, unbiased estimator of this function of the parameter, then the variance of the Tx is at least this one. So we need to prove this one, and the final version is this one. Let Tx is an unbiased estimator of this one. Let's start. It is already mentioned in the statement that Tx is an unbiased estimator of this function. This means that then we can write that E of T of x is equal to this one. Simple. Now we knew that this expectation can be written, this expectation you can expand this or then likelihood, as there are a lot of observations. So this is likelihood dx is equal to this one. This simple steps. Now differentiating with respect to theta, we have now differentiate this with respect to theta. This means that we can write x Tx, and you can differentiate this. This involves theta, the likelihood function. You can write theta here as well, but this involves theta. This is I mentioned here. Instead, it's better to write theta here. But this is of course the function of the sample observation and the parameter theta. But in the statement we mentioned this is the function of the parameter, so we can write like that. But you should remember this is the function of sample observation and parameter theta. So now you can differentiate, apply this one. Dx is equal to simple step. Now again do the same thing. divide by L and multiply by L. Multiply by L now, dx equal to this one. So now you can write this like tx, and this is now equal to partial derivative of this function, that is natural log of L, and to L dx is equal to partial derivative of this function with respect to theta. So this means that, what is mean by this? This means that now this thing is just like the x, the variable, and this is the likelihood function. This, like, you can say x f of x dx is equal to e of x. Just assume this is x. So this means that now you can write this like expected value of, and this thing, this is equal to this thing, partial derivative of this. And you can write this thing, you can write this is equal to covariance of t of x and this thing. This is equal to the covariance of this, which is equal to partial derivative of this quantity with respect to this one. How you can say this? I need to explain. This is important. You know, covariance of x and y is equal to variance of x. You can say this. Covariance of x is equal to e of x and y minus e of x and to e of y. So if you replace this x by dx and y by this one, just write this dx and to partial derivative of this, you can write this, the expected value of dx and to L minus expected value of dx and to expected value of with respect to, and this quantity is equal to 0 from lemma 1. So this is equal to 0, this is equal to 0. So this thing is equal to, this thing is equal to the covariance of this. So this is the simple logic that I can write like this. Okay. So this is equal to covariance, and this you can name equation 1. Now using Cauchy-Schwarz inequality, we have now using Cauchy-Schwarz inequality, we have this inequality is rho xy square is less than equal to 1. This means that the square of the correlation coefficient is less than equal to 1. So this means that you can write this covariance of xy square divided by variance of x and to y less than equal to 1. This means that you can say this is equal to covariance of x y square less than equal to variance of x and to y. Now what we have? Now we have x instead of x, we have x equal to t of x and y equal to partial derivative of this quantity natural log L. Just put these values and you will get this is equal to, now you can just put covariance of t of x, this is instead of x, and this as instead of y less than equal to variance t of x and to variance of this quantity. Now from our equation 1, we know that this thing is equal to, you can see, just see above, this thing is equal to, this is equation 1, this thing is equal to this one, partial derivative of this quantity. Just replace this, you will get from equation 1 what we know from equation 1. From equation 1 we know that partial derivative of this thing with respect to theta, and remember this is square because that quantity is square, as less than equal to variance t of x and to variance of this quantity. Now you can see that you can find the variance of t of x simply. You can write now variance, you can just write inequality in other direction. This is equal to, this will be now greater than equal to square, and now you can find the variance. Simply just divide, you need to find the variance of tx, divide both term by this and you will get variance t of x is greater than square divided by variance like this. So this is simple, that proof which we wanted, we were asked. Or you can see, you see that variance t of x is greater than equal to square, and by the way you remember that this is equal to, this is also equal to this one. This is easy to calculate, you just take the second derivative and then take the expectation. This is now lower bound and this is proved. Now f special case, f this function is equal to theta simple, then this is equal to theta, so the derivative of this is 1, and in that case the variance of this function is equal to, or you can say greater than or equal to minus 1 divided by expected value of the second partial derivative of this natural log likelihood. So this is all about the Kramer-Rao inequality, and which is useful to find the lower bound of an estimator. So this was all about an unbiased estimator. This is an assignment for you. Try this, the same thing. Try the above assignment, or you can say homework. Try the above for biased estimator, please. Okay, so thank you very much. This was all about the Kramer law inequality, and if you like the contents, please subscribe the lecture so that you can receive notification for the latest videos. And thank you very much, and see you in the next video. Ciao.